The first question typically asked is, why should I invest the time and the money to develop simulation models? Why can't I just use causal loop diagrams or relationship models? And while there is a lot that one can learn from relationship models, there are times when the risk associated with inappropriate action is so great that it's actually worth spending the resources, the time, the money, to develop a, a better understanding of the implications of the relationships. And there are certain questions that you can only answer with simulation models. I mean, from a qualitative diagram, you can get a sense of what the relationships are. Though, if you ask questions about how much or how long for any of the components, that there's no clue from a static diagram. You need a dynamic model that unfolds over time that gives you a sense of how the relationships play out. And here's a couple of examples. Here's a model of a consulting organization that has two types of employees. It has rookies and pros, and it keeps track of how many of each there are and the revenue generated by them. And it has a policy so that for every pro that quits, it hires a new rookie, and it takes 6 months to train a rookie to become a pro. And the organization has been in a steady state operation for a long time with 120 employees, 60 pros and 60 rookies, and it's generating a stable revenue. And things have been fine. It's been constant for so long that nobody actually pays attention to it any longer. Though all of a sudden in month 17, someone looks and notes that there seems to be an awful lot more rookies around than there are pros. And the revenue is down, so they start looking for the problem. And where do you think they look? In week 17, of course, because that's where they noticed the situation. I've talked before about the fact that we live in a world of events, and we think about things in the now as opposed to transitions over time. Though when they actually start looking, they find out that the problem actually occurred 6 months earlier in month 10, where the number of quits changed from 10 to 15, the pros, and for every pro that quit, they still hired a new rookie. So they still had 120 employees. It's just that step change in one variable set off a 6 month transition period so that pros went from 60 to 30 and rookies went from 60 to 90, and revenue dropped off accordingly. And this is the kind of thing that you simply can't find or begin to understand from a qualitative diagram. Here's a model of performance in an organization where there's an actual performance and a desired performance, and the difference between them creates a performance gap. Typically, the options are that one or the organization can choose that performance gap as pressure to do work, and they spend more time working to improve their performance, so they work harder. The alternative is to take that performance gap and use it as a pressure to improve their capability, so they spend time on improvement and improve their capability, which improves their performance. Though the pressure to do work typically detracts from the time spent on improvement, so that their capability erodes, so they erode their reinvestment over time. And by doing that, because they're eroding their capability, they look for shortcuts to keep up. So in this model, there's a number of different alternatives for actually fulfilling the performance gap. But if you ask questions about how much do you invest, what are the implications of working harder instead of smarter, and what's the capability erosion, this model will not answer those questions. If you develop the same model as a simulation model, you can look at it and understand that it begins in a steady state, and when you introduce a increase in the desired performance, the choices, if you decide to work harder, then the cost of operation goes up, the time spent working goes up, but after a period of time, the actual performance declines because of capability erosion, which is the reason that they're working more and more and the cost of operation is increasing. If they chose to work smarter as opposed to harder, and they invested time on improvement, then the cost of operation goes up. The the actual time working goes up, but then after they invest in that improvement, the cost of operation declines, the actual time spent working declines below what it previously was, and they meet their performance goals. Though in this situation, things got worse before they got better. The alternative is to go ahead and sort of split the effort and do some time working harder and some time working smarter so that it's sort of not as exaggerated as the previous diagram, so that you do some investment in improvement and you do spend some time working harder so that the cost of operation goes up a bit, performance increases, and then the cost of operation comes back down. So it's calibrated for a particular environment, and one would have to calibrate it for a different environment, though it begins to give you a sense of how things change, and you can't understand these kinds of things from a static picture. Now, one might say that this is because this is a very complex or complicated environment, and that's why you need a simulation model as opposed to a qualitative model. It doesn't, this kind of predicament doesn't only happen with very complex models. Here is probably one of the simplest structures that you can create. It's a typical balancing loop where there's a current state, a desired state, and the difference between the two creates a gap, and the gap is the impetus for action to move the current state in the direction of the desired state. And in here, there's the option to introduce a time delay. If we run this with no time delay, we get the typical characteristic behavior for a balancing loop where this is the goal, the current state starts out at 0 and approaches the goal as the gap gets smaller and the action declines. And now the question is, how does this curve behave if I introduce a time delay? Well, if I introduce a time delay of 1, you notice that the current state actually overshoots the goal because of not realizing the implications of my actions. And you actually have to invest effort to bring the current state back to the desired state. And if you continue to increase the time delay, you end up with a damped oscillations. You finally get to where you want to be, but you're fluctuating back and forth. Think of this as the situation of an impatient person trying to adjust the shower back and forth. It takes time for it to settle out, and if you're impatient, you're turning the hot and cold water too far to get to the point that you're looking for. And with sufficient time delays, the behavior never settles out, and even longer time delay, the behavior of the structure is actually out of control, so that it gets further and further away from the goal over time. Now, some might say that this is a bit unrealistic. How can you have that kind of a time delay in the structure? Well, think about trying to control the motion of the Mars rover. And the picture that you have of where the rover is 9.5 minutes old. And if you issue a command for it to turn, it takes 9.5 minutes for the command to get there, and another 9.5 minutes for you to get an image of what happened. So it's worse than driving in the rearview mirror. You're driving 18 minutes, 19 minutes old, simply because of the time delays. So there are situations where we specifically need to know answers that we cannot come to understand from qualitative models, And the only way that we can develop an appropriate understanding is by developing simulation models. And throughout the rest of this course, we'll go ahead and present how to develop simulation models in Insight Maker. So hope you found this informative, and I'll see you in the next video. Bye.